Good morning, Math 20-2s. Today we're going to look at lesson number 2 in the trig unit, which has to do with the sine law. So if you remember from Thursday and Friday, what we looked at is we looked at trigonometry using SOHCAHTOA. So using the sine, the cosine, and the tangent ratio in right triangles. What we're going to look at in the next couple of lessons is what happens if the triangle is not a right angle triangle. Can we still use SOHCAHTOA? And the quick answer to that is no, we can't. We can't use SOHCAHTOA when we're not dealing with a right triangle. So what we can do is we can take a triangle and make it into a right triangle, or we can find or see if there's some other relationship. So if we take a look at the following class example, we have triangle ABC, which is not a right triangle. It has an angle of 75 degrees here, if I took the 20 and the 55 and added them together, and an angle of 35 degrees here. Which means, first off, we could find out what angle B is. We could use our 180 minus the 75 and the 35, which would give us 70 degrees. So that angle B would be a 70-degree angle. So from here, we are asked to determine the length of BC, this whole length. Well, if I split this up and I look at it as two separate triangles, triangle ABD and triangle ACD, I could find the lengths from B to D and D to C, which together would give me the entire length of the triangle, or of that section of the triangle. So let's start off with AB, or ABD. I have an angle here that was given to me of 20 degrees. I have a side length that was given to me, which is the hypotenuse of that triangle, because it's opposite the 90 degree. If this is 90 degrees, the other side has to be 90 degrees, because they're supplementary, they form a straight line. And what I'm trying to do is I'm trying to find this side here, which we call the opposite, because it's opposite my 20-degree angle. So my trig function that compares opposite and hypotenuse is sine. So if I find the sine of a 20-degree angle, that equals the opposite side, which is labeled BD, to the hypotenuse, which is 12.5. I can then solve for side length BD by multiplying both sides by the 12.5. That will get rid of the dividing by 12.5. So 12.5 times sine 20 will give me 4.275. If I want, I could have a couple more decimal places just so that when I do my final rounding, I'm still maintaining or trying to be as accurate as possible. So now I have this measurement. So the next measurement that I need is this line segment from D to C. Well, if I take a look at this triangle ADC, I have no information. I have no information other than the angles. I need a side length. I need something. So what I can do is go back to this triangle here and notice both triangles share the side length of AD. So if I could somehow figure out the length of AD, I could then use that in the second triangle. So again, I have an angle. This time I have its adjacent side and the hypotenuse. So that would be cos. Cos of a 20-degree angle equals the adjacent side, which is labeled AD, to the hypotenuse. So again, to get AD by itself, I do the opposite of dividing by 12.5. I multiply by 12.5. And when I put that into the calculator, I get an answer of 11.746, which again goes on. It's not exactly 11.746. It does continue on. Now that I have that angle, that side measurement, I can use this side measurement at either one of these two angles to find out DC. So if I started off with my 35, in comparison to 35, this is called the adjacent side, the opposite side, and this is the adjacent side. If I already have this labeled as adjacent, I might find it easier to just go this way. This is my opposite side, and that is my adjacent. So the trig function that compares opposite and adjacent is tan. So the tan of a 55-degree angle, because that's the angle I'm using, is the opposite side, which is the length from D to C, over the adjacent side, which was this 11.746. So again, because I'm dividing, I get rid of the division through multiplication. So if I take that 11.746 and multiply it by tan 55, I'm going to get the length from D to C, which is 16.775. So then my final step will be to find the length of B to C by adding these two values together. 4.275 plus 16.775, which once I've added it together, I got to 2 decimal places, 21.05 meters. A lot of steps to do this question. I needed to find the length of BD, I need to find the length of AD, and then use that to find the length of DC, and then I had to add them all together. Mathematicians like to find patterns. They like to find if there's another way that we could come up with this result. And that's what they've done. What they discovered was a relationship exists between the sine of an angle and its opposite side. So before we get into that relationship, we need to be able to label these triangles. If you've noticed over the last couple of years, whenever you look at a triangle, the vertices, that's the points of the triangle, are always labeled with a capital letter. CAT, XYZ, ABC, they're always capital letters. Then the side lengths, I can refer to the side length in one of two ways. I can say this is side length BC, using the vertices, or this is side length little a. This is side length AC, or little b. And this is side length AB, or little c. So how do I know where to put the A and the B and the C? Well, if you look at this diagram, the A and the B and the C are opposite those vertice points. So using that notation, what was discovered is that there exists a relationship between the sine of an angle and its opposite side. In fact, if I go the side divided by the sine of its opposite angle, that will be the same for every corresponding pair of sides and angles. And it doesn't matter if I go side divided by angle or angle divided by side. It will still give me that same relationship. So I can have all my sine A, B, and C on the top, or I can have them on the bottom. And I can use this to help solve equations. Before I get to the solving of the equation, we need to look at proving why this is true. So if you remember, when we're doing proofs, we have to look at deductive reasoning. So we're not looking at examples with numbers, we're looking at variables. We're looking at making it true for any circumstance. So we take triangle ABC. We place AB along the x-axis, and we draw it two ways. We draw it the first way where the vertex A is on the origin, and then we draw it the other way where the vertex B is on the origin. Remember, opposite angle B is what we call side B. Opposite angle A would be what's called side A. So what we're going to show is we're going to show that A over sine A is equal to B divided by sine B. So if I look first of all at this triangle right here, if I was to think of this right triangle, ACD, the sine of angle A is the opposite over the hypotenuse, the opposite being CD and the hypotenuse being AC. But I can rearrange AC, or substitute in the value of B for AC. Then, if I get CD by itself, I do that by multiplying both sides by B. That's how I get rid of the divided by B. So B times sine A. That's what side length CD would equal. Now, if I go to the next triangle in the other picture, I have triangle BCD. And this time, if I look at sine of angle B, is the opposite, which is CD, over the hypotenuse, which is BC. But instead of writing BC, I could write side length A. And if I wanted to isolate CD, instead of dividing by A, I'm going to multiply by A. That'll get rid of the A on this side. And then I multiply by A on the other side. So I get A times sine B. Both of these results were equal to CD, which means that if CD equals this value and CD equals that value, these two values have to be equal to each other. And then if I took those two values, I'm going to write it up here because there's more room to show you. And if I divided them by a sine A, sine B, as long as I'm doing the same thing to both sides of the equation, I'm not changing the value, so I could divide both sides of the equation by sine A, sine B. The sine A's will cancel on this side, and I'll get B over sine B. And the sine B's will cancel on this side, and I'll get A over sine A. And I could repeat this process by changing the triangle and putting AC along the x-axis and CB along the x-axis and doing the exact same thing. And then I could show that A over sine A equals B over sine C. And it follows, if A over sine A equals this and A over sine A equals that, these two values have to equal each other. And then I get the bottom relationship. This formula is on your formula sheet. You do not have to memorize it, but we do need to be able to use it, which is what the next couple of class examples will look at doing. So you'll be able to stop this video and then start the next part for the class examples.